Today we're going to talk about friction. This is a tough section. The reason it's tough is this. So there are definitely people in this room, and I was always one of them too, who was able to get through physics by just knowing the equations, plugging stuff in, and using the equations to solve the problems, but not necessarily always sort of understanding the concepts underlying it, okay? So you can't do that with friction. And added to that, friction is tough because it's a little more abstract for a few different reasons that we'll get to. So anyway, my point is you need to stay on top of this, all right? As soon as you start feeling like, whoa, what's he talking about? Then stop it, all right? So today my goal is to get through, we're going to learn there are two types of friction. There's static and kinetic friction. My goal is to at least get you up through the equation for static friction, and then tomorrow we'll probably have to do some examples and stuff. But like I say, if we can kind of knock some of this stuff out today, it'll give us more time to work on the problems tomorrow in class. All right, so here we go. So friction. You guys have seen this definition before. I think it was in the first chunk of notes this chapter when we defined forces. Remember that I listed different types of forces? All right, one of them was friction. So remember, friction is the force applied by a surface an object is in contact with, okay? Now remember though, you guys, friction sort of serves two roles. Okay, so sometimes friction works against the motion of an object that's already sliding across the surface, right? Like if I take this chair and push it across the floor after asking you to move your feet, please. Thank you. The reason that didn't slide into the desk is because friction slowed it down, right? It was already sliding. Friction worked against its motion and slowed it down. Thank you, Tom. So that's going to look like this. You're going to have some sort of object. It's already sliding, so I'm going to label that arrow with a V for velocity. And friction goes, whoa, 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 whoa. I don't want that thing to slide anymore. What are you doing? I don't want that thing sliding. What are you doing? I'm going to push this way with some force of friction to stop it. All right? The name for that kind of friction that tries to work against an object that's already sliding is called kinetic friction. So we tack a little K on it to indicate kinetic, right? The word kinetic is physics speak for moving, right? Yes. Yes. All right. Is everybody good up to that? Okay, now, sometimes friction doesn't act against an object which is sliding, it acts against an object that is sort of attempting to slide. For example, this table here, if I push on it with a little bit of force, it still doesn't move, right? Well, what's preventing it from moving? There's got to be something preventing it from moving. Otherwise, it would be moving that way, right? It would be accelerated. Okay? And so this is what's called static friction. Right? Static friction is what prevents an object that's sort of trying to slide. It prevents it from sliding. Okay? So that's going to look like this. You're going to have an object sitting on a surface. You're going to have some force, maybe it's the force of Hecker or the force of Roy or whatever, that's trying to get it to move, trying to get it to slide, but just with not enough force to overcome that friction. So in that case, what's preventing it from moving is it's still friction, but now it's called static friction. Okay. Yes.
Is static friction always going to be the same amount of whatever your initial force is?
Yeah, let me see if that is true. No, not necessarily. Not necessarily. Most often, for the purposes of this class, that will be true, but in the real world, not always. And actually, we'll do a few examples where it's not true. Okay, so, and there are even a couple examples here in the notes where that works. All right, so, but do we understand the two differences? Yes.
When writing the K and the S, in addition, would you like us to kind of subscript it again?
Technically, it's supposed to be subscript. I just can't type that with this stupid program. So I don't care. That's a nitpicky thing. All right, so are we good? All right, now, the thing I want to caution you about, well, I'm getting ahead of myself. All right, so those are the two types of friction. All right, so here are some things that you need to know about static friction. All right, so first of all, Static friction only occurs if the object is not sliding. I want to emphasize this word sliding across the surface. But the object would slide if static friction wasn't there. Okay? So look, when I push this table, if there wasn't any friction, it would slide, wouldn't it? Like if this was on a hockey rink, which is made of ice, this would probably slide, wouldn't it? Okay? But it's not sliding because friction is preventing it from sliding. All right? But I want to caution you because a lot of times people then go, oh, if it's not moving, then it's static friction. And that's not exactly true because weirdly, static friction is what allows you to walk. It's what makes cars go. Right? Because think about it. When you press on the gas pedal, you're asking the wheels to turn, right? Why are the wheels made of rubber? So they grip the road, right? So instead of the wheels just spinning and you not moving anywhere, static friction prevents the wheels from slipping against the road, and that's what pushes the car forward. So there's an example where there isn't anything pushing the car backwards. It's static friction pushing the car forward. Does that make sense?
Yeah.
So static friction isn't about moving or not moving, it's about sliding or not sliding. Static friction occurs when the two surfaces are not sliding against each other. Make sense? Right, and then walking is the other example, right? When you take a step forward, you're hoping that your shoe doesn't slip against the floor, right? That's why it's hard to walk in socks on a wooden floor, right? Your feet just slip and you don't go anywhere, right? Or dogs, right? On wooden floors, right? Okay, so, everybody good with that? Okay, all right. Now, here's another important thing that you need to know about friction. It's lazy. Static friction specifically is lazy, and it's going to exert as little force as possible to prevent the two objects from sliding across each other. Okay? Oftentimes, and this kind of gets to what Maddie was asking before, oftentimes that means your net force is going to be zero, but not always, as is in the case of the car. But here's what I'm talking about. Look, suppose I push on the desk with 1 Newton. Oops. 1 Newton, there we go. Doesn't move, right? So that means I'm pushing with 1 Newton, it's not moving, net force is 0, so my force of static friction must be negative 1 Newton, right? If I push with 2 Newtons, I'm pushing harder, but it's still not moving, right? So static friction is now exerting 2 Newtons, 3 Newtons, 4 Newtons, 5 Newtons, until eventually I'm able to overcome it, right? Okay? So what that means then is this. It turns out that when two objects sort of rub together or are tried to rub together, there's not a technical name for this, unfortunately, but there's a maximum amount of force that static friction can exert. All right, I'm going to call this FFS, force of static friction, max. So that's a subscript and subscript and subscript. All right, so FFS max, force of friction, static, max. All right, that's like the most force that static friction can exert in that particular example. All right, and what that number is, what that maximum friction is, depends on 2 things. The first thing it depends on is what the 2 surfaces are that are rubbing together. All right, 2 pieces of ice rubbing together are going to have much less friction than, a rubber tire on a cement road. Okay, so how that's measured, that sort of roughness, it's measured using what is called a coefficient of static friction. All right, the symbol for coefficient of static friction is this weirdness. All right, it's the Greek letter mu. All right, so what it looks like a lowercase letter u with a little like tail on the front end. All right, usually when I draw it, I just kind of do swoop and then like that. All right. So it's the Greek letter mu, and that stands for the coefficient of friction. Specifically, we want the coefficient of static friction, so you put a little s there. And obviously, in a minute, we'll have coefficient of kinetic friction. All right, so that coefficient of friction, that mu, it's a ratio. It doesn't have any units, and it's just sort of a measure of how rough the 2 surfaces are. All right, the lowest coefficient of friction you could have would be 0. Okay, and in the real world, that doesn't exist. You can get close to 0, but nothing is perfectly 0. All right, and then anywhere around 1 is very high. All right. I realized I wrote down the common example of this. It turns out that most tires on a dry, I don't know if that's cement or blacktop or what, but in general, tire on a dry road, your coefficient of friction is going to be about 1. There are examples that are higher than 1. I wasn't smart enough to write one down, so I'll have to look that up. So anyway, these are some different examples. Teflon on Teflon. Teflon is slippery, right? That's why your pancakes don't stick your pan. All right, so if you put Teflon on Teflon, the coefficient of static friction is 0.04. Ice on ice is 0.1. Tire on a wet road is 0.6. Tire on a dry road is 1.0. Okay? So notice, I didn't give you any information about the objects except what they're made of. All right? Because this is happening on a molecular level. So if you imagine a Teflon surface and a Teflon surface, because it's Teflon, that's going to determine sort of the molecular structure of those two surfaces, right? Remember on the first day we talked about this, we talked about pieces of sandpaper, right? Teflon on Teflon is going to be like very, very low grit sandpaper, right? It's going to be very smooth when you rub them across each other, okay? Whereas because tires are kind of squishy a little bit, the rubber squishes into the cement, right? And it results in a higher coefficient of friction. Cool? Yes.
So is that like the inertia of the molecule that you're sliding against because you bump into it?
Ooh, no, not exactly, because when you talk about the inertia, you're talking about the mass. It would have to do more, so here it starts to get into some chemistry, and it would depend on sort of the molecular structure of the object itself, like the bonds holding the molecules together. And, what's that? I don't know, I haven't been in chemistry in 100 years.
Yeah.
But yes, it's what's holding the thing together. And then added to that, how sort of smooth is it? You know what I mean? Like, do the molecules form little bumps or? Exactly. All right, so that is one of the two things that matters, the two surfaces that are rubbing together. All right? And then the second thing that matters is how tightly the two surfaces are being pressed together. All right, you guys have all seen this. Look, it gets cold in the winter, you rub your hands together. So do this. Put your hands lightly together and rub together. All right, so you can feel it. Maybe it starts to tingle a little bit. But your hands aren't really getting warmer, right? So now what I want you to do is push harder. Like press your hands together harder and then rub. And they get hot, right? Like you can feel it getting hot. Come in. Hello? Okay. Do you know where it is? Oh, is it back there? Oh.
Yeah.
Okay, cool. All right, so did you guys all notice that? When your hands are pressed tightly together, and you rub them together, they get hot, right? Can you guys feel that? All right, that's friction. But notice it's more when you hold your hands together tight than if you just press them light and they don't get as hot. Okay? And yesterday we learned what that force is. That's the normal force. Okay? That's why, so like if you've got a heavy object sitting on a surface and you try to push it, the reason it's hard to push isn't necessarily because it's heavy. The reason it's hard to push is the fact that it's heavy means there's a large normal force and therefore a lot of friction. Okay? So, those are the two things. So it turns out then that to calculate the maximum force of static friction, you take your coefficient of friction, which remember that's just a ratio with no units, and you multiply it by the normal force. Okay? And then your force of static friction is always going to be less than or equal to that, because by definition, that's the max. Cool?
Friction. So the force of friction max equals that.
Yeah, so this here represents how much force static friction is exerting. Good? You okay with that, Christina?
Yeah.
Thank you for asking this. I think I did not make this clear. So this FFS, when you write FFS, you're talking about how much force static friction is exerting on the object. Okay? I like is exerting better than exerts. All right, so that's how much force static friction is exerting within the context of your problem. Whereas this number here is how much force static friction can exert. That's like the maximum amount that it has in its belt. Cool? So it's like if you can lift 150 pounds, then the maximum you can lift is 150 pounds. That doesn't mean that every time you lift something, you only lift 150 pounds. That's just the maximum you can exert. Okay? Maddie, and then Willie.
Can you explain one more time why normal force is in the equation?
Why it's in the equation. So I keep using it. So in my old building, I had this. It was a cabinet that was sort of like in the front of my room, and it was what I always used to do these friction illustrations. And for me to push it, I really had to push it. You know what I mean? Like here, I keep doing this. Just this table's not that heavy. You know what I mean? And because it's not that heavy, there isn't that much sort of force pressing the table into the floor
Okay.
to create that extra pressure that results in extra friction.
Okay.
Follow? Like pushing those molecules together, right? Now, if I weigh it down, that creates extra pressure between those molecules, and as a result, it makes it harder to push it forward. Harder, it's increasing the friction.
Okay, so the more force of gravity there is going to be.
Well, technically, it's the normal force, but in this case, if there's more gravity, there's also more normal force, right?
Yeah.
Because if something weighs more, then the ground has to exert more force to hold it up. Follow?
Yeah.
Okay. Because so remember, you guys, normal force is the support force provided by the surface, and friction is the sort of rubbing force between the object and that surface. So you know what I mean?
Yeah.
Okay. Max, did I answer your question?
Yeah,
Okay. What were you going to ask, just out of curiosity?
I was gonna ask, since it's relying on the normal force, does that mean gravity would affect it if it's on the ground?
Yeah, exactly. Exactly. Right. So what that means, just to put this in perspective a little bit, look, if you've got a car sitting on wet cement, on dry cement, car sitting on dry cement, and you're like, I need to move this thing. You've got two options. You can pick it up and move it, or you can slide it, right? Or I guess you can drive it, but ton of cars are locked and parking brake is not. Things are difficult, right? It turns out, remember I told you that coefficient of static friction was 1? All right. Well, your normal force is going to be equal to your weight, right? That means it's just as hard to slide a car as it is to lift a car. If it's on,
Well, if the wheels don't.
if it's on dry cement and the wheels don't roll, and yeah.
So, could you say that one thing again? You have this U-looking thing.
Mu, it's the Greek letter mu. It's spelled mu. So like delta is D-E-L-T-A, right? Is a Greek letter. That's the Greek letter mu, and it's spelled mu.
And it's always 1 when it's static?
No, no. So there are a bunch. You sure?
Yeah.
Okay. There's different coefficients of static friction depending on your two materials. Good. All right. Okay. So I was hoping to get through an example. We obviously didn't. So tomorrow I'll pick up here. I'll re-explain this, and then we'll jump into some numeric examples so you can kind of see this in practice. All right. Whatever you didn't finish of worksheet